Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. Apparently you have to actually hit the notification bell to get notifications for this series and many others. What we're going to do today is we're going to do a short and condensed version where I try not to, we'll see, no promises, but I'm going to try not to do all the math calculations inside there. I'll just give you bullet point ideas of the mathematically modeling of the coronavirus or other infectious diseases. For the coronavirus, basically a bunch of scientists and papers have been put out, and I've looked at a bunch of these papers, etc. And from each disease's case specific, how you're going to model it. But essentially in all the diseases, you're going to start off with a total population N. From that total population N of individuals, in this case human individuals, but it doesn't really matter. It could be a disease in any kind of species, and then you just talk about the individuals in this species. Coincidentally, corona came from bats originally, so they had to model it in the bat population, and then in some host population, which was some unknown mammalian species possibly, and then it got into the food markets, and then it got into the human population. We're going to focus on the human population N. From that, we immediately, and that's why we're going to call them compartmental diagrams, we're going to separate the total population into who we believe is the main players in the population or categories of people in there. For us, what we usually have is susceptible individuals, we have exposed individuals, and what that means is a lot of the times we'll just talk about SEIR models. We're going to add an E in this one because this E category is how you add in latency period. I'll talk about latency in a minute, but essentially what latency means is you can have the common cold or coronavirus, but you can't spread it yet. You're exposed to it, but you're infected, but not infectious. This will be, the I's will be the truly infectious individuals that can now spread the disease to other individuals, the susceptibles. We're going to see how they interact, and then they're going to interact to create exposed people. And from this, we have a removed category, which is, or recovered, depending on the disease. You either recover or removed from death or other means from the disease scenario. I know, well, we're trying to do some math and just ruining everything. Okay. All right, this is Petra. It's just like a parent. I do have real kids too. So cats are your pets. They all got the same. I know. This is Jasper. She's messing with stuff in the background. Okay. She's reminding me that I'm not supposed to do a bunch of the math. I'm just supposed to stick to explaining how it works, not doing all the details. All right, so basically from dividing the total population into categories, we had susceptible individuals, exposed individuals, infectious individuals, and recovered individuals. We literally put them into compartments, into boxes. Then what we're going to do is draw a bunch of arrows from the boxes. We've sat at a table and with a committee and decided that based on this and based on the disease, we pick where arrows should come in and out of them. Let's draw those arrows and then I'll explain where we're going to get these from. We're going to have these types of arrows. And then we're going to have these ones. You don't want to be coming out of those ones. And then we're going to put directions on them. What that says is this is a population flowing in. This is the total population. You can think of them in a box. There's a bunch of people in there. And how do you get new ones? Birth rate is usually what that's going to be. And then from this, once an infected individual comes in contact with those infected, you're going to go into this category. You're going to be exposed to the disease. Once you're exposed and you've gone through your latency period, then what you're going to get is truly infectious. So you would move from that box to this box. Once you're infected for a certain amount of time, a common cold, 7 days or whatever, you recover from that and are removed from the category. So then you come out of there into this box. And in this, time waits for no model or man. These will be natural death rates. We're going to have now, let's label these so we could have natural death rates coming out of these. We can add an actual extra little term for the death rates here possibly, but we won't. Then we add a bunch of, this is where we get parameter values. So here comes the parameters. Lambda, they're all going to be Greek letters. Lambda is the constant birth rate of new individuals who can be susceptible to the infection. Then in here, we're going to have beta SI, not EI. Then here, we're going to have epsilon E. Then here, we're going to have a gamma I. And then in here, we're going to assume that we have a delta S, a delta E, a delta I, and a delta R. What are those things? Let's explain them in detail. right now. So magic, there they are. What we want in each of these categories at this stage, once we have the compartmental diagram and the arrows of flowing on how we're going to have the populations are going to change over time, how do you get into the new box or how do you get out of the box, which are representing populations, we now make guesses at how that's actually happening. Here we're going to assume that the total new influx of individuals is a constant. This may also depend on time and it may change over time, but in models you want to basically simplify as much as you can and then expand in detail to answer specific questions. In most cases, it's assumed that this is roughly a constant birth rate, especially in a local period where we're going to talk about trying to nip coronavirus in the butt. But don't touch butts, it's coronavirus. When we're trying to stop coronavirus, we're talking about, hopefully, I'm hoping, a 6 month to a year period where we have to do this isolation business and then it'll be over. In that year period, we're going to assume that the birth rates of the human population didn't get affected that much, so it's roughly constant. Here now is a little bit confusing if you don't do the mathematical modeling on a daily basis. Susceptible individuals are going to go from being okay to having the infection, whatever it is, the coronavirus. Basically right here you have the coronavirus if you're in either box. The difference between these two boxes is a lot of the time we just get rid of this box entirely and just have SEIR models. This is the latency period. Sometimes you get the disease but you can't infect other individuals for a certain period of time. Scientists call that the latency period. So latency is how long you have the infection but are not infectious to give it to other people. We assume that infectious people are moving around in the population, and so are these guys. And then when two of those guys, you can watch one of our other videos, in fact, in the series of coronavirus, we explain in gory detail how to get this mass action bilinear incidence term. But we have an infectious individual moving around and a susceptible individual, and sometimes they come in contact, and sometimes that contact produces a new infected individual. And we're saying that, roughly speaking, this is how you would move from being susceptible to being exposed and having the disease. Two of these guys have the contact at a rate of beta is the contact rate. And so 5 and 6 are discussing this term. Beta is the contact rate, and beta SI is the bilinear mass action, how we think everyone's being mixed around and interacting and creating new infectious individuals. Epsilon E is what we're saying is you are moved from being exposed to truly infectious at a rate of which is proportional to the total population, and we call that epsilon. Epsilon is the latency transfer rate. Basically, 1 over epsilon is the average time that you are infected but not infectious. Same thing here. We assume that gamma is the recovery rate from being infectious to being recovered or removed. 1 over gamma is going to be the average time that you were infected. For a common cold, again, 1 over gamma would be 7 days. Roughly is what they're going to calculate. That's what the gamma is meaning in our parameter values. These are all called parameters. And the last one, there's actually 4 of them, but we simplified to call them 1, and we're assuming that the death rate is constant and it's all the same for each one. You'll see why that helps us in deriving feasible regions and stuff like that. If it's not, these equations get much more complicated. These are the compartmental diagrams, and these are the parameter values that we're going to use in more sophisticated models. These parameters get larger and larger in number. Basically, this is what we think mathematically is describing coronavirus spreading through a population. From the compartmental diagram now, we saw all those parameter values. Don't worry about them. We've set it up that we're trying to make it as realistic as possible to what we really think of how the disease is spreading through our population. Remember, this is the total population, and this right here actually, unbeknownst to you, is one city's population. Then we've got hundreds and millions of cities and a bunch of, it gets complicated. And then we'll talk about, eventually in this series, we're going to talk about connected networks of differential equations of this happening in a bunch of populations everywhere. And then we'll talk about couplings and how it just spreads from geographic location to another geographic location. But coincidentally, it should be pointed out, this is the disease spreading through one geographic location, not through the world right now. This is just in one population fixed. If you want to talk about the Earth being the whole population, then okay, then now we're back in N. In that scenario now, we can derive what we call ordinary differential equations. As scientists, what we want to now say is these populations are S is we're looking for functions mathematically that will describe over time how the susceptible population is growing or decreasing, increasing or decreasing, and exposed, infectious, and recovered individuals. From these diagrams, so that says the population is changing. If you don't know anything about calculus, what this symbol means, ds dt, is the derivative of s with respect to time. You're like, that explanation didn't really help me very much. All you need to know is ds dt or de dt. Anytime you see one of those symbols, a derivative of something with respect to time means that I'm looking for its change over time. How is it changing over time? And that's exactly what we're looking for. We put a few infected individuals into a susceptible population. We want to know how that starts changing over time. So we need to get functions which model those things and then explicitly solve these differential equations. Wait till the cat's doing whatever they're doing in the background. We're shooting videos in here. Hello. Then what we're going to do is, from these compartmental diagrams, we can derive differential equations, which means how are the populations changing over time. It's actually quite easy once you have the diagram. Arrows going into it give us a positive term in the differential equation. Arrows coming out give us a negative term, and this is how I built these equations. Now we have a system of 4 nonlinear ordinary differential equations and 4 unknowns, and this is where it gets extremely hard to start magically calculating and finding a solution to these things. But from the compartmental diagrams, we derive differential equations, and now it's the job of the mathematicians to solve these things. Let's do that. I won't show you the details, we're just going to give you an idea. Actually, these ones I can't solve explicitly. We'll do it in the other videos. I do explicitly, but eventually you have to use approximation theory and Runge-Kutta and these types of things. Solving nonlinear differential equations is difficult. Let's look at the analysis. Before we erase these, I want to remind you also, if you haven't done this and don't do this on a daily basis like us mathematicians do, I was perfectly okay with discussing what a solution meant, but maybe I should point out what a solution actually means to these things. From the real world, scientists create differential equations from different scenarios. From this now, what we mean by a solution to this differential equation is we're looking for a set of functions s of t. They're all going to depend on time, but they're describing our susceptible population, our exposed population, our infectious population, and our removed population over time. And what a solution means is we find 4 functions which satisfy these ODEs. They behave this way, and they satisfy the initial conditions where at time 0, before we start analyzing the model, we have an initial population of susceptible individuals, exposed individuals, infectious individuals, and recovered individuals. So that's what we mean mathematically to solve these things. And if you look at some of our other videos, I actually explicitly show you the techniques of separable variables and a couple of things to actually explicitly show you how we do solve these things. I'm not going to do it in this video, but that's what we mean by it. I'm looking for now 4 functions, SEIR, which are all functions of time, which satisfy these ODEs and have the initial populations of these. Let's do that magically. In these ones are so complicated and nonlinear enough where we can't actually give you explicit solutions to them anyways. So what we're going to do now is, instead, we're going to set these all equal to 0 and look at what we call equilibrium conditions. Let's do that. Because these ODEs in this one specifically, because of the way that we've tried to make it a realistic model for the coronavirus, we can't, and I'm not going to show you the techniques of what they try to do in the differential equations to try and solve explicitly or implicitly or otherwise to get approximations using Runge-Kutta algorithms and these types of things for these nonlinear differential equations. In the simpler cases, we can explicitly do that, so I do in the baby models to show you what the technique in the process is, but this drastically quickly breaks down because they become complicated and we can't find explicit or implicit solutions a lot of the time. What we do instead is have to analyze we don't just give up, hence the error, I guess we're going to quit. What we do instead is look at different tactics, and a major tactic in differential equation theory is looking at equilibrium scenarios. Equilibrium means that there's no change in the system. No change means that in mathematically, derivatives describe change, remember. And if we're saying there's no change and an equilibrium state, that means the derivatives are 0. Before we do that though, so we're going to look at when the derivatives of zero, remember these all had equations. This one was lambda minus beta si minus delta s, and this, they all have equations, so we're going to set those equal to zero. And then what we're going to do is we're going to look for when these are zero, we may be able to find s and e and I and r and find explicit values based on the parameters of what they're going to look like as numbers in the population. Before we do that though and look explicitly for the equilibrium equations, we're going to find a feasible region quickly. Basically what that means is we want our total population to be positive. And cleverly what they do is, I just put it in here to show you, we want the total population to be positive, the change in the total population. Mathematically, also in Calculus 1, when you take your first calculus class, the derivative being non-negative in an interval means your function is increasing. So that's what that means, is to have our derivative non-negative means that our total population is increasing, which is what we want over time. So to have that logical requirement, we can use these equations and open this up cleverly and put all those in there and set them equal to zero, and we can derive a feasible region for in 4 space for the 4 functions that we're looking for now. Remember, these are 4 functions which are positive, and they're in, so we talk about them being in 4 space. This is the region where if you have s plus e plus I plus r is less than lambda over delta, this would mean that your total population is actually increasing, and this would be a reasonable region to look for a solution for this differential equation business. Basically what we're saying is, to have a real world interpretation and a meaningful interpretation to this math mumbo jumbo that we're doing, we have to have that the solutions better be in this region, otherwise it wouldn't make sense in the real world models. Good. Now what we're going to do from this feasible region business is solve these explicitly and try to find out when we would have equilibriums where we have a disease, or equilibrium states where we don't have a disease. Let's do that. From Equilibria, what we're saying is we're setting all these equations equal to zero. Once we do that, we're going to basically, with some experience in analyzing it as mathematicians and stealing it from my supervisors, Michael Lee and Jim Muldowney, there's a whole story here that we haven't actually told you. Once we have these equilibria in the 2 cases I'm about to do, we have to talk about global asymptotic stability of equilibria in the feasible region. And this is using Lyapunov functions and all kinds of mathematical theory to prove that these have stable equilibria, chaos theory and these types of things. So there's a whole scenario we haven't actually talked about in this, more mathy stuff. But for now, essentially what we're trying to say is, in the feasible region, we want to look at when we would have equilibria. From some experience, we notice immediately by staring and being frustrated and being stuck at not being able to explicitly solve the ODEs and not knowing where to go, but with my hands in the air to being like, what's going on here? We stare at these equilibria equations a bunch of times, not these ones, but the useful ones that have the equations lambda minus beta si equals 0. You move them around and manipulate a little bit, and what you see is I star depends on E, and R star, we put stars also to say we're at equilibrium, not in the general population. This is the no change state. And we notice that I depends on E and R depends on E. And what that does, if you think about it for a second, is all we have to now focus on is E and S, because I and R are immediately dependent on those 2 guys. So case 1 is what we do is we say, well, what if the exposed individuals is 0? If there are no exposed individuals, that immediately tells us from these 2 equations that the infected population is 0 and the removed population is 0. All the populations are 0. And when you calculate using the first equation, you can see that S star now would be lambda over delta, which is a positive real number. Remember, this is some real number and this is some real number, so the ratio of that tells us how many susceptible individuals, a number of people we have at equilibria. From this, essentially we get what we call the disease-free equilibrium. This means that once the disease has moved and there's no change in the populations anymore, we could have one scenario where if the E star is 0, both I star and R star will be 0. There will be no exposed, no infectious, and no removed individuals. There will only be susceptible individuals, and this is what the population will look like with no disease in the population. This is the scenario we want in general. And in a lot of cases, you'll see it's bipartite. There's going to be case 2. What if E is not 0? Then there will be, this is not 0 and this is not 0, and there will be another equilibrium. Let's do that one now. All right, the other case is the case that we're currently in with coronavirus. We definitely have an endemic or a pandemic. What's the difference between pandemic and endemic? You look it up, we'll do it in a different video. Not telling you now. If we have that the exposed population is not 0 in case 2, then we immediately saw, because I and R also depend on that, these two guys are non-zero. And if you look at these equations again and analyze them, S star is not 0 also. So we have a completely positive solution where the S and the E and the I and the R are all positive. In the last one, we had a non-negative solution where only S star was positive and the other 3 were zeros. This is right near the on part of the boundary of that feasible region. Now what we have is completely in the interior of that feasible region, we have what we call an endemic equilibrium. Again, I'm going to skip all the details this time, but if you solve these ODEs when you assume that this guy is not 0, you get that you can solve for S star is specifically, remember these are all parameter values, these that were set in the system originally, these are all numbers, so S star is a positive number, and now E star, I star, and R star are all now positive numbers, and this is what we call the endemic equilibrium. It's in red because this is the bad one. This is the one we don't want, and this is the current state that we're in. We have a pandemic, which means it's globally across the world, and then it's endemic if it never completely leaves the population. So this would be at equilibrium in case 2. If we have that the exposed individuals are non-zero, we're definitely going to have an endemic equilibrium where all the populations are positive, and then we try to analyze and see how we could mitigate and make these as small as possible and make this one larger by looking at the solutions. The last thing we're going to do is, because of this scenario, we want a tipping point as to see where eventually would the susceptibles eventually grow and win this tug of war, or are the infected individuals eventually going to win? We want this one to decrease, of course, and this one to increase in a good model, if we can mitigate and try to rectify the scenario. From that, what are we going to do? Let's now derive the general reproduction number. Okay, for the general reproduction number, where is this coming from the models? Essentially, we would like this, we just saw that there was 2 scenarios. If E star is 0, we have what we call the disease-free equilibrium, which is what we want. And then if E star is non-zero, everybody's non-zero, and we have a disease or an endemic equilibrium. What we want, of course, is the no disease outbreak. For that to happen, we would have to have that the susceptible population is larger than or equal to lambda over delta. But we now have an explicit formula from the equilibrium equations. We can derive what S star is explicitly, just numbers now, from our parameter values. What this tells us mathematically is, if we have this condition, we just put this hot mess into where S star was, and we get this inequality. And what that logically now tells us is, based on our parameter values from our system of all these flow, remember this was the constant birth rate and this is the death rate, remember, and then all these guys had values of interpretations in the model. From those parameter values now, we have a condition on and an inequality which we can control, which will now say, if this inequality is true, then we have no disease. And so let's look at this inequality. And what they classically do is they're going to make this equality, they're going to make something less than 1. If they can make this thing, all these parameter values less than 1, we would have no disease. And that's what they're going to call the general reproduction number. Let's do that. Okay, so basically what we have now, we had this inequality. I rewrote it at the top. What that says is all these things are positive quantities, so adding them and multiplying are still positive quantities. I'm checking anytime I multiply both sides of an inequality by a number, is it going to flip the inequality? No, this is entirely a positive number, so I'm going to multiply by the inverse of it, and it won't change the inequality. So I do that, I multiply it here, I get beta epsilon lambda over delta plus this hot mass blah 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 is less than 1. That is in fact what we call our general reproduction number for this model. Why? Because if this quantity, these are the parameter values that we had in our system originally. If we take those parameter values and have that in combination in this quotient, that it's less than 1, we have disease-free equilibrium, which is what we wanted. So this is where they get in the models and they start saying, we're going to call R naught beta epsilon lambda over delta epsilon plus delta plus gamma. And why are they doing that? Because now they can say if R naught is less than 1, we get a disease-free equilibrium. If we have that 1 is strictly less than R naught, if R naught is larger than 1 now, that would do the reverse. By default, this would say we have endemic equilibrium. So this is where they'll define the general reproduction number, and then they say this is essentially the tipping point. If R naught is less than 1, we get disease free, and if R naught is larger than 1, we get endemic equilibrium. What my supervisor Michael Lee and Jim Muldowney did in the mid-90s, 1995 I think is the first seminal paper, they give global asymptotic stability of both the disease-free and endemic equilibrium in those regions in both of those cases. And so then now we know not only do we have these two scenarios, but mathematically it's stable asymptotically, so it's we're going to call well-behaved, and all solutions sort of gravitate towards those equilibrium positions over time. Please subscribe right here and hit the notification bell. You'll get notifications for this series and many others. You can follow us at Adrian the Tutor on Facebook or Tutor_Inc. on Twitter. I'll see you next time. Rainbow drop. Did I have the coffee? I can't remember anymore. Coffee, no coffee, no coffee. Doesn't matter.